Okay, welcome back. So, if you recall, in the last lecture I had stopped at a stage where I derived the specific heat of an ideal Fermi gas. So, the answer we obtained were these. So, the specific heat at constant volume was found to be proportional to temperature, and so there was a relation between specific heat at constant pressure and constant volume, which was of this nature. So, and also we derived the equation of state of an ideal Fermi gas at low temperatures. So, recall that this is applicable at low temperatures. By low temperatures, I mean temperatures small compared to mu f, and if you remember what mu f was the chemical potential at absolute 0. So, that is also known as Fermi energy. So, the chemical potential at absolute 0 is known as Fermi energy. So, the specific heat at constant volume is proportional to temperature at low temperatures, and this is a hallmark of basically what is called the electronic contribution to the specific heat of a solid. So, so the electronic contribution comes from the fact that fermions are solids contain fermions. I mean, they contain electrons as in their orbital. The orbitals of the atoms that make up the solid contain electrons, and the electrons contribute to the specific heat of the solid, and their contribution is governed by Fermi-Dirac statistics. So, we have been successful in showing that the specific heat contribution of the electrons to a solid is proportional to the temperature at low temperatures. Okay, and also at low temperatures we can derive what is known as the equation of state, and you can see that at low temperatures unlike so there is a dramatic departure from a classical ideal gas. So, if you recall the classical ideal gas was PV equals NT. So, this is for a classical ideal gas, this is regardless of what temperature I am talking about, this is always true. But then you can see that as temperature is lowered, the pressure. So, if you fix the volume and fix the number of particles, as temperature is lowered, the pressure actually falls of a classical ideal gas, but not so for a gas made of fermions. So, if you have a quantum gas made of fermions, and so even though it is ideal, it still has this dramatic departure from a classical ideal gas, and the origin for this I have already explained. It is because of Pauli exclusion principle. So, basically what is happening here is that if you start at 0 temperatures, for example, for a classical ideal gas at absolute 0 the pressure is strictly 0, but then for a Fermi gas at absolute 0 the pressure is not 0 for the simple reason that we have already shown that PV is so regardless of whether it is Bose gas, Fermi gas or classical ideal gas, PV is just 2/3 times the total internal energy. So, it just so happens that at absolute 0 the total internal energy of a classical ideal gas is 0, because basically at 0 temperatures all molecular motion cease, and so the molecules basically come to a standstill, and they can do that because they are classical particles. So, you can have simultaneously the positions being independent of time and velocities being 0. And however, that is not true for quantum gas. So, what happens is that at absolute 0 the system is in the ground state, and then because they are fermions they obey Pauli's exclusion principle, which means that you can't really populate the 0 momentum state with more than 2 particles. So, if you have a macroscopic number of particles in your system, then you are forced to you can at most accommodate 2 particles in the 0 momentum state, and immediately you will have to go to the next higher state, which will bump up the energy, because if it was strictly 0 momentum state, and you know that energy is p squared by 2m, and you can still get total energy is zero if those electrons were there in the zero momentum state. But then given that only 2 electrons at most can be accommodated in the zero momentum state, so we have a macroscopic number of electrons. So the question is, where do you accommodate them? So we start accommodating them in higher and higher momenta. So by accommodating them in higher momentum states, we are gradually increasing the energy of the system. So when you reach when you exhaust all your electrons, you would have reached a very high level of energy, and that's called the Fermi level. So the Fermi energy. So now you can calculate the total energy contained in that system, which will be enormous, and that's the reason why the pressure is also significant, because it's going to be proportional to the Fermi energy, and the Fermi energy is typically huge for a Fermi gas at absolute zero. So this is so there's a name for this type of pressure. It's called the degeneracy pressure, and it so happens that this degeneracy pressure is actually the reason why white dwarfs, the stars, there are stars in the sky that are known as white dwarfs. So white dwarfs are stars where the nuclear fusion has ceased. So all the nuclear processes that say, for example, our own sun is still burning bright because there is a nuclear fusion process that's taking place, which is releasing huge amounts of energy, which is contributing to the pressure that counteracts the gravity that's trying to shrink the star into a point. So the gravity is always present, but then the pressure that's responsible for counteracting the gravity is not going to be always present. It's going to be present so long as those nuclear reactions take place. But then you know that how nuclear reactions work. The lighter elements get converted to heavier elements, and so on and so forth. So once you start running out of lighter and lighter elements, the nuclear reactions, or there's a fusion reaction, slows down, and a stage is reached where it ceases altogether. So the moment nuclear fusion ceases, then there's no the pressure that's contributed by those reactions also becomes zero. So now when no pressure is available to counteract gravity, so gravity takes over, and the star shrinks and shrinks and shrinks. So now the big question is that does it shrink to a point immediately, or is there some mechanism, some other mechanism besides nuclear fusion that takes over, that prevents the star from collapsing to a point? So it so happens that there is a mechanism, and that was famously discovered by the great Indian astrophysicist S. Chandrasekhar on his voyage from India to England on a ship. So he thought about what could be those mechanisms, and he knew about quantum mechanics and Fermi gas and that sort of thing, and he realized that the mechanism could be precisely the degeneracy pressure. So you see, once the nuclear reactions cease, then all the matter tries to collapse to a very small region of space due to gravity, and all the atoms get squeezed together so tightly that the electrons dislodge from the atoms, so they become part of a collective. So they start becoming like a gas. So there will be a gas of electrons which propagate through the entire star. So that's precisely what Chandrasekhar studied, and so he imagined that there is a gas of electrons which have been dislodged from the atoms which are propagating through the entire star. So there is going to be a degeneracy pressure. So if you try to compress them any further, because there is this pressure due to the Fermi level, the Fermi energy of those electrons causes them to resist that shrinking any further. So there is going to be a stage where the radius of the star reaches an equilibrium value, where the pressure, the degeneracy pressure, which is trying to prevent the star from shrinking any further, is cancelled by the or is counteracted by the gravitational pressure that's trying to shrink the star. So there's a gravitational force which is trying to pull it in, and there's a counteracting pressure, a force due to degeneracy, the Pauli exclusion principle, which is trying to counteract that. When the two balance, there's an equilibrium, and that equilibrium is reached for a certain radius of the star, and in fact more importantly for a certain mass of the. So Chandrasekhar derived his famous Chandrasekhar limit, where he showed that there is an interesting upper limit to the initial mass of the star. So this mechanism, this equilibrium mechanism is mathematically feasible only if the mass of the initial star was not too high. So if the mass of the initial star was too high, his equations predicted that there would be some instability, and so Chandrasekhar famously said that so this mechanism cannot support the star, so the star would then collapse to a point. And okay, I don't want to spend too much more time on the Chandrasekhar limit right now, because I'm going to be discussing probably the details derivation of the Chandrasekhar limit a little later. So this is just a preamble for you to understand the importance of the equation of state of a ideal Fermi gas. So it has a huge implication to various fields, subfields of physics, such as astrophysics and so on. Okay, so now let's get to the the counterpart of what we have been just studying, namely the Bose gas. So we have studied the ideal Fermi gas. Now let's go ahead and see if we can study the ideal Bose gas, and that has its own interesting features, as you will see. So unlike the Fermi gas, where there is a huge pressure even at absolute zero, that's not going to be the case in ideal Bose gas. But then, so even though it's similar to classical ideal gas in that sense, but there's still a huge difference between a classical ideal gas and a classical Bose gas, and the difference comes in what is known as Bose-Einstein condensation, which is peculiar to ideal Bose gas. So let me go ahead and discuss these issues. So if you recall, for bosons, this Q, which was the parameter that determined the quantum statistics, was actually going to be -1. We had to select it to be -1. So if you remember, if we selected Q to be +1, we would be describing fermions, and then just by coincidence, if I set Q to 0, I would be describing a classical Boltzmann gas. So now given that Q is -1 corresponds to bosons, now I am called upon to evaluate such an integral. So if you recall, this parameter n has only two interesting values. One of them is 0, the other is 1. So when it's 0, this integral would be corresponding to basically the total number of particles in the system as a function of z, which is the fugacity. So I'll be discussing the density, as it were. So the density of particles related to fugacity is obtained by evaluating this integral for n equal to 0. So the integral would correspond to the total internal energy of the system. So I would be studying the energy density of the bosons as a function of z, which is fugacity. But then besides this integral, we had something else we had observed, namely this ratio that I am talking about here, that is 1 by e raised to beta times z raised to -1 this ratio, this has a physical meaning, namely it corresponds to the number of bosons in energy level epsilon j. And given that this is the average number of bosons in that energy level, it has to be greater than 0, because it can't be certainly less than 0. It can be 0, but it can't be less than 0. So what I should be demanding is that the number of bosons in energy level epsilon j had better be greater than or equal to 0. And given that z is e raised to beta mu and beta and mu are real numbers, then you can see that log z is beta mu, which is of course also real. And since beta is greater than 0 and epsilon greater than 0, and this has to be valid, so you can convince yourself that all this put together means z has to be between 0 and 1. Okay. So, so it can't be more than 1. So what does that imply? So that implies that since beta is greater than 0, that implies that mu has to be less than 0. So in a Bose gas, typically the chemical potential is always less than or equal to 0. Okay. So that's the same as saying z is between 0 and 1. So now let's consider two extreme limits. One extreme limit is where z is really close to 0. Z is always greater than 0, of course, but let's imagine that it's very close to 0. So if it's very close to 0, so recall that because if z is very close to 0, this number is huge. So the leading contribution, and that's in the denominator, so the leading contribution is going to be proportional to z. And then I can do my expansion in powers of z, and the term proportional to z will involve this integration over this variable, and the term proportional to z squared will involve an integration of that sort. So when I do that, so and so on and so forth. So now when I do this integration, I end up with this answer. So you can see that it's proportional to z, and there's another term which is proportional to z squared, and so on. All right. So this is my gamma function. If you recall, if n was integer, and it is, because n is either 0 or 1. So if n was integer, it would be n minus 1 factorial, but then this is n plus 3 halves. So you have to use an appropriate generalization of the factorial function, which is what is called the gamma function. So I urge you to look it up if you don't know what it is. We have encountered this before, by the way. All right, so now let's I'm going to make use of this. So remember that I told you that if n is 0, I'll be using that for evaluating the density of bosons. So, so the density of bosons is going to be this, and if you recall, C0 is my notation for the thermal wavelength, which is more commonly denoted by lambda t. Okay, so most of the other books would call it lambda t, because I started off writing C0. I didn't want to change my notation midway, so I'm continuing with C0. So that's basically the thermal wavelength. All right, so now the density of bosons is going to be this, and I put in my expression for C0, and I get this for the density of bosons as a function of the chemical potentials, assuming the chemical potential is very close to 0. And by the way, what does that correspond to? Not the chemical, fugacity. So, so this only correct when the fugacity is very small compared to 1 and greater than 0. So in other words, it's very close to 0 and positive. So what does that mean in terms of the chemical potential? So if the fugacity is very small, it means that the chemical potential is large and negative, because remember that fugacity is nothing but e raised to beta mu. So since beta is positive and z fugacity has to be really small, that means that mu is large and negative. So remember that all the expressions that we should be handling should have the number of particles and volume fixed. So rather than having a situation where the fugacity or the chemical potential is fixed, so even though this method kind of naturally allows you to study a system where the number of particles is fluctuating, that is, the particles are being exchanged with the environment in addition to energy. So, but I want that's a less usual situation. The more usual situation is when only the energy is being exchanged with the environment, but the number of particles in the system is fixed. So if I want to go back and forth between the two pictures, it's going to be possible in a natural way. It's going to be possible to do that with the same formulas would describe either situation, only if you remember, there was a condition that those two pictures are going to be equivalent only if you are working in the thermodynamic limit. So in other words, it only works for large systems where you can ignore fluctuations. We have discussed that earlier. Okay, given all these caveats, I can go ahead and invert this relationship and write down expression for the fugacity in terms of the density of particles. So given that fugacity is small, that's the same as if temperature is fixed. That's another way of saying that the density is small. So that's a dilute system. So I'm looking at the dilute limit of a Bose gas. So it's also the class. So if you fix the density, Z has to be very small. So if Z is very small, there are two ways of doing it. Either you make rho very small or beta very small. So how do you make beta very small? You make beta very small by making temperature very large. So Z very small has two different interpretations. One is the interpretation that Z is very small means rho is very small, because these two are related. And rho is very small is the same as studying a dilute limit. So that means the number density is very small, means there are very few bosons in your volume V. Alternatively, if you don't want to do that, you can fix the number of bosons in your system to be as many as you want, but then you have to pay the price that if you want to make Z very small, you have to make beta very small, which is the same as studying a very high temperature limit of the Bose gas. So that's also the classical limit. So you can see that dilute limit is the same as the classical limit. So you can see that that's also the same as h bar tends to 0. So if you choose not to do either of these, you fix rho, fix beta, and you still want Z to be small, the only other way is to make h bar tends to 0, which of course you can't do in nature, but I mean mathematically you can see that that's equivalent. So Z being very small is the same as either thinking of the dilute limit where rho is very small, or if you don't want to do that, you think of beta as very small, which is the same as high temperature or the classical limit, or alternatively the other version of the classical limit is h bar tends to 0 where rho and beta are fixed. Alright, after that long preamble, so let me get to the thing which I want to study. So I am going to find the energy per particle. So I have to divide the expression between the total energy of the bosons divided by the total number of particles. So when I do that, I get this expression, and remember the Z is really small. So because of that, the leading contribution to the energy per particle is precisely the classical result 3/2 T. So remember that the energy per particle of a classical ideal gas is 3/2 T, because its U is 3/2 NT, but per particle is 3/2 T. So that would be the leading contribution here, and there's a quantum correction caused by the fugacity, and which can of course be expressed in terms of density. So this is the classical limit of quantum Bose gas, okay, a semi-classical limit. The strictly classical limit would be this would be the leading correction to the classical limit. All right. So now let's discuss the other extreme. So remember I told you that Z, the fugacity is always between 0 and 1. So what I have studied is one extreme limit where Z is close to 0. So I can study the other extreme where Z is close to 1. Of course, you might be wondering, why am I studying various limits? Why not leave Z as it is? The answer is that of course the general expressions are already there, but the point is they are not illuminating, they don't teach you anything. It's some ugly looking formula that you have to stare at and believe. So by studying limits, what you're doing basically is that you're trying to get a feel for the subject. You're trying to see what happens if I increase this parameter keeping the others fixed, what type of physics am I recovering from that, or does the system go to this situation or that situation? So that's what you're trying to gain a deeper understanding of those formulas themselves. So it's not, physics is not just about deriving formulas, it's about getting a feel for what those formulas mean practically. All right, so in order to do that, I just finished studying the limit where z was close to 0. So now I'm going to study the other limit where z is close to 1. So that's the same as saying 1 minus z is close to 0. Z is close to 1 is same as saying 1 minus z is close to 0. And remember, 1 minus z is positive because z is less than 1. Okay, so now if I go ahead and naively expand in powers of 1 minus z, I just remember that I had to evaluate this. And if I just decide to think of 1 minus z as a small quantity and try to expand in powers of that, I will be disappointed, because of course I am going to get this, which makes some sense, but I am going to also start getting something bigger in the denominator, and that is going to cause divergence for small values of r. So all the higher terms are going to diverge. So implying that there is some kind of an singularity at z equal to 1 is some kind of a singular point that I can't really expand. And I mean, it's a false assumption to say that you can expand in powers of 1 minus z. So that would be possible only if your answer were an analytic function of 1 minus z. So what this is telling you is that it is not, which is why all these coefficients are diverging. So now the reason why it doesn't work is because, so this is trying to tell you something, that when r is small, so when z is close to 1, the r equal to 0 is going to be problematic. And in fact, what you can do is you can start off with remember that this was really the expression for the total number of particles. So I am kind of deliberately separating out a term which corresponds to epsilon j equals 0. So why am I doing that? I am always allowed to, I mean, this is a mathematical identity, I can always do this because put together this is sum over all epsilon j. And the reason why I am doing this is because you see, when z is close to 1, this is going to be divergent. See, if z is not close to 1, this is some number of the order of unity. So if z is between 0 and 1, so suppose z is half, this is some uninteresting number of order unity. But however, this is proportional to the size of the system, because it's the rest of the energy levels, it's the sum over the rest of the energy levels. So if z is not anywhere close to 1, then I might as well ignore this in favor of this. So separating out this term doesn't really give me anything. I mean, there is no mistake or benefit to doing this. So if z is not close to 1. But the point is that as z starts approaching 1, you see, there is going to be a stage which is reached where this quantity is going to be as important as this quantity. So as you approach z tends to 1, this was huge because it was proportional to the size of the system, with the sum over all the energy levels except one of them. So it's still proportional to the size of the system. And this was going to be of order unity for the most part, except when z tends to 1, it's also going to start increasing until a stage is reached when these two become comparable. And that's the situation I'm interested in. When z is incredibly close to 1, so much so that this is of the same order, the first term which I have separated it out is of the same order as the rest, which is proportional to the size of the system. So in other words, when epsilon j is not 0, there is no singularity in the denominator. Now I can with impunity replace the summation with integration, because with the confidence that it's not going to be mathematically ill defined, there is no divergence because now r is not 0. So it's safe to do this thing. this correspondence. So, so now it so happens that this has a particular name that we can assign it to, or a notation. We denote this by N0, and N0 is what is known as the number of bosons in the condensate. So, remember that it is some kind of a number, because this is the total number of particles, and this is the total number of particles, not including epsilon j equals 0, and this by implication has to be the total number of particles with epsilon j equals 0. So, that is called the condensate. That means if there are macroscopic number of particles with epsilon j equals 0, that is what is known as the condensate, and that phenomenon is known as Bose-Einstein condensation. So, now let us see what we can do with these formulas, and so it so happens that now I can evaluate this integral by expanding, of course, not in integer powers of 1 minus z, but then I have to appeal to my knowledge of this polylog function. So, I am going to skip this derivation. So, you can just do it yourself on some symbolic algebra package like Mathematica, and you get your, if you do it without any further assumptions, it becomes the polylog function, and so it is polylog 3 by 2 comma z, and then you expand that polylog in powers of 1 minus z, and you will see that Mathematica or any of those symbolic packages will tell you that the leading term is this, the next leading term is non-analytic in 1 minus z, which is why you are getting all those singularities when you try to do a Naive-Taylor series. So, the Naive-Taylor series does not work in this case, because the dependence is actually non-analytic in 1 minus z. So, because there are no, it is not just integer powers, there are half integer powers as well. Okay, but it so happens that you can write down this series. Now, when z is close to 1, what this is telling you is that you can, regardless of whether it is analytic or not, you can simply throw away all these terms. So, when z approaches 1, so remember that z approaches 1 is the interesting limit, because as z is breathtakingly close to 1, it is only then when this is macroscopic. Even if z is even slightly far away from 1, this abruptly drops to some quantity of order unity. So, it has to be extraordinarily close to 1, otherwise what we are saying will be uninteresting. So, if z is extraordinarily close to 1, we can certainly drop all this, and in which case we end up with this result, that the total number of particles is the total number of particles in the condensate, which is, remember, now macroscopic, times the volume of the system times the universal constant, and of course, it involves the thermal wavelength here. So, it so happens that this is now, we can write down an expression for this ratio N0 by N, which is the fraction of bosons in the condensate, as a ratio of total number of bosons in the system. So, you can see by definition that fraction has to be between 0 and 1, and then you can derive a formula for that condensate fraction, as it were, and you can express it in terms of the temperature, because remember that this was thermal wavelength, which was dependent on temperature in this fashion, and you can go ahead and re-express the condensate fraction in terms of temperature, and then you can write it in this compact and appealing form, where the condensate fraction becomes 1 minus the temperature in units of some characteristic temperature called Tc raised to the 3/2 power. So, so this is a very classic standard result in Bose-Einstein condensation, and this characteristic temperature scale depends on the density of bosons in your system, and this is known as the Bose-Einstein condensation temperature. And if you are wondering what this funny symbol is, this is nothing but a zeta function. You don't have to strictly know what it is, because after all I got it from simply using my symbolic package to expand this in powers of 1 minus z, and it just gives me these funny looking numbers. And they're not funny to a mathematician, they know it very well. They're called zeta functions. And but then if you want to know numerically what it is, it's 2.612 etc. I mean, it's approximately 2.612. So as a result, the Bose-Einstein condensation temperature is the density of bosons raised to 2/3 times a whole bunch of constants. So you can see that I can also express my z in terms of the temperature, and this is very clear that z is 1 unless T starts to approach Tc. So for so long as T is less than Tc, so this only works at low temperatures. So low compared to Tc, this whole formalism. So when temperature is less than Tc, immediately remember that this n is huge. Because n is huge, this thing is less important. So immediately this becomes 1. So it's only this is going to break down only when you really are close to Tc. So for the most part, z is 1. So I'm just, this is a consistency cross check. So don't pay too much attention to this. The important thing is this one. This is the condensate fraction as a function of temperature. So you can even plot this. So it's going to look like this. I forgot to plot it, so I can plot it right now. So it's going to look like this. So this is my Tc and this is 1. So when at absolute 0 it looks like this, then it drops, and then at Tc it becomes 0. So now you can just repeat this activity for, so remember we just did this for the total number of particles or the number density of the particles. Now you can do the same thing for the energy density of the particles, the similar Taylor series. Then here too you get a non-analytic, I mean the first term appears analytic in 1 minus z, but the very next term is not. So even here you can't really do a naive Taylor series. So now you can rewrite this in terms of, remember that z is breathtakingly close to 1. So that is amplified by this correspondence, which tells me that 1 minus z is 1 over n naught plus 1, where n naught is the number of bosons in the condensate, which is enormous, and because of that 1 minus z is incredibly tiny, which is why I am entitled to ignore them. So I am entitled to ignore this term, etc. So as a result, I am able to write down my energy in the system and relate it to temperature, so long as temperature is small compared to Tc. So when temperature is small compared to Tc, the enormous number of bosons in the condensate, and yes, I am able to do this. So if I know the relation between the total internal energy and temperature, I can write down the specific heat at constant volume. Remember that volume is fixed in my analysis till now. So by definition, I am calculating the specific heat at constant volume. So when I do that, I get a result which says that, well, it's the specific heat at constant volume is proportional to 3/2 the temperature raised to 3/2. Because remember that there's a beta raised to 3/2 there and there's a beta outside. So the energy density is actually proportional to temperature raised to 5/2. Okay. So and du by dt is proportional to temperature raised to 3/2. So that's how it works. Okay. So now I can rewrite it in terms of, I can get rid of all these horrible looking constants and re-express it in terms of this nice thing which we have called the condensation temperature. And there's this interesting looking formula that emerges which says that specific heat of an ideal Bose gas at low temperatures is proportional to temperature raised to 3/2 measured in units of the condensation temperature. So as a result, I can do the same thing with my total internal energy. I can re-express it in terms of Tc rather than those ugly looking constants, which now that I know the total internal energy, it allows me to express or write down my equation of state. So, my equation of state is this: PV equals 2/3 U. Remember that this is always true. PV is 2/3 U regardless of whether I am studying classical gas or Bose gas or Fermi gas, so long as they are all ideal, and as a result the energy versus momentum dispersion is p squared by 2m in all three of them, all three cases. And lastly, I am working in 3 dimensions. That means my gases occupy 3 dimensions of space. So if they somehow occupied only 2 dimensions, this is not going to be valid anymore. This was specific heat at constant volume. But then if I want to get specific heat at constant pressure, what I should be doing is calculating what's known as enthalpy. So if you remember, I explained to you what that is earlier, and there's a formula for that, which is U plus PV, and that's going to be 5/3 U, and then the rate of change of enthalpy with temperature will give me specific heat at constant pressure, and that's 5/3 the specific heat at constant volume. So now just for sake of completeness, I am going to study the case. So this was when the temperature was less than Tc, when there was a macroscopic number of bosons in the condensate. Now imagine that temperature is larger than Tc, but not so large that the system approaches the classical limit. Okay, if it approaches the classical limit, then of course it's we have already studied it. So now imagine that the temperature is slightly more than Tc, in which case then all of a sudden there are absolutely no bosons in the, or there will be only of order unity bosons in the condensate. So the number of bosons in the condensate is no longer macroscopic, it's only a few. So now I can go ahead and study, I want to study what happens when the temperature is slightly above Tc. So in order to do that, so remember that general formulas were these. So that density was related to Z in this general fashion, and the energy per particle was related to Z also in this general fashion. So now what I should be doing formally is getting rid of Z and expressing it in terms of rho and T and putting that back in here, and the energy is going to be function of temperature and density of bosons. So as a result, I am being called upon to invert this relation, which tells me that Z is related to, so I have called W times this whole bunch of numbers, I mean rho times the density of bosons times the whole bunch of things like this. I have given it a new name, I have called it W. So now I am being called upon to invert this, so I write Z as a function of W, because then I can go ahead and substitute that here and there. Then I will be getting, because W is rho and temperature, so I will be expressing energy per particle in terms of density and temperature rather than this unusual looking object called fugacity. Okay. So question is how would I invert this? So this looks formidable, because especially when this polylog function is a little bit unfamiliar to me. Inverting this is going to be even more unfamiliar, but fortunately there's a general method for doing that, and so that goes by the name of Lagrange inversion theorem. So it's nice to know these things, because you never know when you will use them, because maybe in this example it's not that important, but there will be a stage where you might require it, and if you don't know what it is, you won't be able to use it. So the Lagrange inversion theorem is very interesting. What it says is that, so imagine that there's a equation like this which I want to invert. So that means W is f of Z, and I want to write Z in terms of W. So I want the inverse, so that I want to write Z as f inverse W. But imagine this is possible to do only if, so this is going to be possible only if f is analytic in Z at some value of So let's assume it's z equal to 0 that I'm talking about. So imagine that f is analytic around 0. So what that means is that I can do a Taylor series around z. So in other words, the implication is f can always be written like this. So if f cannot be written like this method doesn't work. So if imagine that f can be written like this. So if f can be written like this, then it so happens that that Lagrange inversion theorem guarantees that z can be written in terms of w in this fashion. So you can write z explicitly as w minus f0 raised to n by n factorial times a coefficient which can be calculated. So Lagrange inversion theorem gives a formula for that coefficient as something like this. So, the limit as z tends to 0 is n minus 1th derivative of this ratio. So, now I can go ahead and apply it to my polylog function. So, remember that I wanted to invert this w equals polylog 3 by 2 z, and question is how do I invert that? I use the Lagrange inversion theorem, and I am able to write f of 0 polylog 0 when z is 0, polylog is 0, because remember polylog is z plus z squared by 2 raised to s, where if here s is 3 by 2. So, it is z Li 3 by 2, refresh your memory, z plus z squared over 2 raised to 3 by 2 plus z cubed over 3 raised to 3 by 2 plus dot 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 dot. So, if z is 0, this whole thing is 0. So, as a result, this f of 0 is 0. So, I can write z in terms of w in this fashion, where these coefficients can be computed explicitly, but unfortunately you can't compute the nth term. You can just list them one by one for n equal to 1, this is for n equal to 1, this is for n equal to 2. So, for g n equal to 1 is 1, g n equal to 2 is minus 1 by root 2, like that. So, I have listed a whole bunch of them. I mean, I didn't do this by hand, of course. I just used my favorite package, which is called Mathematica. It just churns out all these numbers. So, clearly this method works certainly well for dilute systems. So, in which case w becomes this, and so for dilute systems we already know how it works. But what is more interesting is this. So, if z is close to unity, then how does it work? So, the general relation is that so when z is close to unity, I can always write like this. Okay. So, that is what this says. So, even though it works well for dilute system, it does not mean it does not work at all when w is close to 1. So, it kind of works even otherwise. So, when w is this and Li 3 by 2 is w, I can go ahead and write this relation. So, now if I expand close to 1, so I write z as 1 plus z dash and t as close to Tc. So, remember t is larger than Tc, but close to Tc, and because z is always less than 1, z dash has to be negative. Okay. So, it is negative and small compared to 1, because then 1 minus z is close to 1 and less than 1. Alright, so now if I expand in powers of z dash and also in powers of t dash, so then I get this expression. Okay, so and z becomes so I can rewrite as z in terms of t minus Tc, and that allows me to cut a long story short, I end up getting a relation for the number of, there is a total energy per particle to be this. So, why did I do all this? I mean, seems like a lot of work. For what reason I have not told you yet. The reason is the following. Now that I have spent so much of effort and got an expression for the total energy per particle for temperature slightly more, right, than the condensation temperature, now I can go ahead and ask myself what is the specific heat of this Bose gas slightly more than the condensate temperature, and that comes out by just differentiating this with respect to temperature, and I get this answer, and this answer is actually the same as what it is for T slightly less than Tc, T close to Tc but less than Tc. So, it so happens that the specific heat across the condensation boundary is continuous. So, the specific heat does not change abruptly. Okay. So, only the total internal energy changes abruptly, but the specific heat does not change. Okay. So, so now we can go ahead and write down, just let me consolidate my formulas here. So, one can use this U that I have derived. So, remember that PV was 2/3 U in general. So, I can use that to write down my PV, the equation of state for Bose gas and Fermi gas as follows. So, when T is less than Tc, my PV is related to temperature in this fashion. When T is greater than Tc, it is related to temperature in this fashion. And when T is much larger than Tc, it is just the classical ideal gas. Okay. So, for an ideal Fermi gas, we can write the equation of state in this fashion, and if for T much less than mu f, it is this, and for T much greater than mu f, it is again the classical ideal gas. So, this is a nice consolidated table of formulas for the equation of state of an ideal Bose gas and an ideal Fermi gas. Okay. So, I am going to make use of this in the next. So, I am going to stop here now. So, in the next class, I am going to make use of these two ideas and persuade you to believe what is known as the virial expansion of the equation of state, which is very useful because in situations. So, remember we have studied only ideal gases. So, if you go ahead and study a gas where there are interactions between molecules, then it is no longer clear because that is a very complicated problem in general. So, if the molecules interact with each other, then it is a hard problem, and but however, you can make some headway into analyzing that through what is known as the virial expansion of the equation of state, which is motivated by just staring at these ideal results we have obtained so far. By consolidating them, which is the classical ideal gas and the quantum Bose gas and quantum Fermi gas. So, by studying these three equations of state, we can kind of guess what the form of the equation of state might be in general. So, that is called the virial expansion. I am going to use that later on, and to motivate the study of a non-ideal classical fluid, which is known as van der Waals fluid. So, I am going to come to that gradually. Okay, I am going to stop here now and hope you will join me for the next class, which is going to be all about virial expansion, van der Waals fluid and so on. Okay, thank you.